So thanks, Agnès, for introducing me, and thank you, Philippe and Peter and everybody organizing this webinar. So today I will present the work the end of the work that was presented by Agnès Salvati that we conducted during the Annex 80 Weather Data Task Force with many institutions. And this work I conducted when I was doing my PhD in Rochelle University in partnership with CSTB. And now I am working for CSTB, which is Scientific and Technical Center in France. So the outline of my presentation will be to first present the future heatwave weather files that we have developed within the Annex 80. And then I will present some of the work I conducted during my PhD about building design contribution using some future heatwave weather files for building thermal simulations with some adaptation strategies and health risk assessment. So first, as Agnès said, we started from the 20 years hourly data set that was bias adjusted, and the methodology that we have used to download the Codex climate data within the Annex was a methodology that I had initiated in my PhD with this paper, and the methodology was improved with Abhishek Gore initiative to bias adjust the weather data sets, which was an important step to detect the heat wave because the bias adjustment affects a lot the extremes of the distribution. So to detect the heat wave, we have many definitions around the world. Every country has its own definition to detect heat waves. And we wanted to find, to use a definition for the Annex 80, which was the same definition for all the cities to have a comparative basis. So we decided to use a method that was developed by Ouzo et al., which are French climatologists, which have used different thresholds, 3 thresholds based on multi-year historical mean daily temperatures, which have been compared with other heat wave detection methods and have proven to be correct to detect heat waves. And this method was applied, was used for France with absolute threshold, and they have made relative threshold for a 20-year historical period of temperature, which means that this relative threshold can be used on other cities to detect heat wave. And with this method, it means that you can detect a heat wave even in Antarctica. It means it's the extreme of the temperature of the dataset. So in France, we have other heat wave detection method. For instance, epidemiologists are detecting heat wave based on past mortality data to detect heat wave based on health risk. And this method I have also used in my PhD, but it's only applied for, since it's mortality data is very local, we decided not to use epidemiologist threshold for the Annex, but only climatologist threshold. But we could see that at least for France, I have compared two methods, and at least half of the heat wave that we detect with the climatologist threshold have a potential health risk in France. So we don't know for the other cities, but maybe similar data can be found. So this is a graph that shows the heat wave, the different number of heat waves that we have found for each of the cities for which we have made the heat wave weather files. So we can observe we have 3 periods, as Agnès already presented, the 2010, which is the contemporary period, mid-century period, and end of the century. And we can see a tremendous increase just in the number of heat waves detected for each city that we have analyzed. We can see that in the contemporary period, very few heat waves actually are found over this 30, I wrote 30 years, but actually it was 20 years. Over the 20 years of analysis, in the contemporary period, around 5 heat waves are found per city. And if we look at the mid-century, cities have around 20 heat waves detected over 20 years, so, or 15 heat waves. So it's 1 heat wave every 2 years, an average depending on the cities. And by the end of the century, we can see more than 20 heat waves detected for each of the city, which means more than 1 heat wave per year. So this is this was very interesting to have made this analysis for all the cities, all these different climate zones, because this data, we are not used to use them for building thermal simulations. And as Agnès mentioned, in data in typical meteorological year that we found in different data generators, we don't find such extreme temperatures, which are more representative of what is most likely going to happen. But this is only for one socioeconomic scenario and one climate model, so we cannot generalize the results, but with the methodology, we still find many, many heat waves. So the heat wave here is a representation of the different heat wave and an example for Los Angeles. So you can see one heat wave is represented by one bubble. On the x-axis, you can see the duration of each heat wave, and the y-axis, you can see the intensity, which is defined by the maximum temperature, daily temperature reached during the heat wave. And you can see for each of the different period, historical, future midterm, and future long-term. And so on the graph on the top is all the heat wave that we have found on each of the 3 periods. And the graph of the bottom is the heat wave that we have decided to select for our building thermal resilience assessment. We have decided to select the most extreme heat waves on each period. So for instance, you can see the largest bubble on the right is the longest heat waves of all heat waves detected for the future long-term period. And the second dark bubble, brown bubble, is the heat wave of the long-term century with the highest intensity and as well highest severity, which is a combination of duration and intensity defined by the bubble size of the heat wave. And finally, some more data on these extreme heat waves that we have decided to use for the resilience thermal assessment. So we have selected the most extreme heat waves. So on the graph of the top, you can see the intensity of the most intense heat wave that we have selected for each city and for each period. And what we can see is that the intensity of the most intense heat wave increases between the different time periods, which was expected, of course, but we can have some general numbers. We can see an increase up to 5 degrees in daily mean temperatures in average in the cities. Some cities, for instance, in Sao Paulo, it's higher than 5 degrees, the increase between the end of the century and now. In some cities, we also observe that the increase is higher between the end of the century and in the mid-century, and some other cities we can see that the increase is quite linear, so depends on the cities. And then when we analyze the heat wave duration, which is the figure on the bottom, we can observe very, very long heat waves, which are projected to occur, especially in the 4 hottest climate zones. And we could already see this with the mean average temperature that Agnès was presenting before. And here we can see that the longest heat waves are more than 2 months long by the end of the century for the hottest cities, and for most of the cities at least 1 month long. And by the mid-centuries, the heat wave duration goes from 1 week to almost up to a month, which is a big change to consider in building design. So this is it for the weather data heat wave that we have developed for the Annex 80. And as Agnès have mentioned, this data will be published in datasets. And what we have presented was only one method to detect heat wave, and we have made EPW files ready for building thermal simulations for these specific extreme heat wave datasets. But the 20 years bias adjusted weather data sets of all weather variables will also be published. So everybody is welcome to use this data to use its own method of heat wave detection, adding other criteria such as relative humidity or solar radiation or any criteria related to specific country that anyone wants to use. So we think there is a lot of potential in reusing these data sets that we will publish. So now regarding the practical applications of these future heat wave weather files during the building designs, here I will present part of my work that I conducted during my PhD. So it was, this contribution was a contribution to a methodology of building design. So you can see here on the graph, which is a how building design is currently made in France. So it's quite a linear way between the sketch of the building and until the design of the building until the project. And then the idea was to propose to add a new objective criterion into the building design. So we design buildings for to maximize energy sobriety, to have reduced energy needs, and to maximize summer thermal comfort. But we also wanted to add a performance objective criterion, which was to reduce the heat-related health risk that can occur during heat waves. So which is why we have developed future heat wave weather files to be able to assess this potential health risk. And then we conducted many building thermal simulation with the use of statistical methods such as sensitivity analysis and building design optimization to optimize different passive cooling strategies. And then we analyzed these optimized building designs during the future heat wave to assess the potential health risk. So regarding the different adaptation strategies that were analyzed. So first we have used a building case study, which was a residential case study building compliant with the latest French thermal regulation, which has an advantageous design for summer thermal comfort, let's say, because it allows cross ventilation, has large windows which can create high airflow rates through the windows when they are open. And also the building has a buffer zone. It has a veranda oriented on the south. So we assume that the exterior windows of the veranda are open in the summer, which actually creates a buffer space for the solar radiation, which arrives in the veranda, but then the direct solar radiation doesn't enter this condition zone in the middle where people are living. So actually this was the beneficial design for this building. And then we have conducted optimization methods between two contradictory objectives, which are to minimize the heating needs and to minimize the summer thermal discomfort. And we have done this for two cities in France. So Paris, the capital, and Carpentras, which is one of the hottest cities in the south. And we have compared three different ventilative cooling strategies, which are in green, mechanical free cooling, which is enhanced airflow rates through the ventilation ducts. Natural ventilation, which was made by windows opening by night. And then an earth-to-air heat exchanger, so the air temperature going through the ground to be cooled. And what we can observe, so on the left of the graph, you can observe Pareto front for the present typical year, and on the right, the future typical year. If we compare the different strategies, we can see that during the present in Paris, we have no discomfort, whatever the solution we're using. But in the future, we can observe some summer thermal discomfort. And in Carpentras, we can also see that in some situations of the Pareto front, when the heating needs are the highest, even though they're very low, we can minimize this summer thermal discomfort in the present, but in the future, we can observe very high increase for all the solutions. Then what we wanted to know was what was the parameters of these optimized building designs. So here I present the configuration with the earth-to-air heat exchanger in the climate of Paris, and we can compare the scenarios, the different parameters of this optimized design on the Pareto front. So if you look at the Pareto front, that is the green line here, that has never any summer thermal discomfort. And you can see, so for the present climate, the optimized parameter here. So they are rounded from 0, they are normed from 0 to 1, and their variation are in the table on the right. And what we can observe is that to reach 0 thermal discomfort in Paris in the present, we can have different glazing percentage configurations. Actually, the glazing percentage only varies with the heating needs. So for low heating needs, we have low glazing percentage, high heating needs, of course, higher glazing percentage. For the thermal mass, for instance, we have high thermal mass that will lead to low heating needs. And vice versa. But then for summer thermal comfort, we can have any of these solutions that will lead to 0. However, in the future, what we can see is that to minimize the summer thermal discomfort, we need to have high thermal mass in the building designs and to have low glazing percentage in the building designs. So for the simulation to see the impact of the glazing percentage, there was no solar shading. And we can also observe for the other weather variables, for instance, this is the properties of the roof for the albedo, the absorptivity and emissivity of the exterior coating of the roof. We can see that we can have different designs for the present, but in the future, if we want to minimize the summer thermal discomfort, we need to have very specific values for this roof optical properties. And the same occurs for the overhang. So all of this to say that in the present, we could reach zero summer thermal discomfort with many building design configurations. But however, in the future, we really need to optimize the building designs on specific designs to minimize this summer thermal discomfort. So this was the results for only the typical meteorological years that we had used to also analyze the heating needs during the winter period. But then we wanted to analyze the heat stress during the heat waves. And the question that we were asked was, which heat wave do we want to use to assess the potential health risk? So here you can see the different heat waves for the city in Carpentras in the south of France. So the graph on the top is for the present period, and the graph of the bottom is for the mid-century. And we can see different, each bubble represents one heat wave. Different colors are for different climate models. And then the question we were asking ourselves was, which heat wave do we want to use? So for instance, the heat waves that are colored in the middle here are heat waves that were found in the typical meteorological years. So we can see that we find some heat waves in the typical meteorological years, but very, very small heat waves in comparison to the different heat waves that can be found during this period. Then we had the choice to use the longest heat wave over 30 years, which is the one on the right, which is, for instance, the scenario that we have used for the Annex 80, or the most intense heat wave, which has the highest intensity on the y-axis, which is also the one that we have used for the Annex 80. But in the context of the work of this PhD, we have decided to use an intermediate heat wave that we were calling a typical heat wave, because we have chosen it with an intensity calculated with a return period every 5 years. So the question that I want to raise here is that in the building design, one has to think about how it wants to design the building and what is the analysis that one wants to make. Is it an adaptation analysis to minimize cooling needs and to use typical years or typical heat wave, or do we want to use extreme heat wave scenarios for more resilience analysis? So here we have present the result that we conducted with health risk assessments under this future typical heat wave, as we qualify it, which was not the most extreme heat wave, but one recurring heat wave during the mid-century. And we analyzed this with the standard effective temperature, which is a very first approach to characterize the health risk. And we can see this standard effective temperature scale in the colors on the bottom right. And then we have compared it for the 3 weather files, the present typical TMY, the future TMY, and the future heat wave for 3 building designs on the Pareto front. With the building designs, A being the ones which has the lowest summer thermal discomforts and the highest heating needs, so always leading to the reduced health risk. AB being an intermediate solution, and B the solution with the highest discomfort and lowest heating needs. And what we can observe if we compare the different solutions is that we have a maximum standard effective temperature, which are the figures on the top of the graph. For the future heat wave, we have much higher maximum standard effective temperature than during the future TMYs, for instance. So this emphasizes the need to use also future heat wave to investigate potential health risk. And when we investigate also nighttime maximum temperature, we can also observe that only during the future heat wave we have elevated standard effective temperature, which was not found using typical meteorological years. And this is, in this weather file, we have not included urban heat island effects. And we know that if we had included them, it would be even higher, the impact during the future heat wave in an urban context, for instance. Another indicator that we wanted to analyze was the number of consecutive days in which we have potential health risk during a heat wave, because usual thermal comfort indicators use sometimes an aggregation of discomfort over a different specific period. But for heat stress, we know that it is the consecutive exposure to indoor heat that will have an effect on the metabolic, on the physiological body. And here we have decided to use a low threshold of 25.6 of standard effective temperature, which is of course subject to discussion, but it was a first approach and we decided to use this low criteria, this low threshold to account for more vulnerable people. And we can see on the bottom for 3 cities in France and the different ventilative cooling solutions and the different building designs, then using this threshold, we always have at least 1 week of consecutive potential health risk according to our definition. Finally, I just wanted to add a word on the impact of occupant behavior on the summer thermal discomfort and potential health risk, because we know that occupant behavior has a tremendous impact on the heating needs, but this is even more predominant in summer designs and even more in new energy efficient buildings. Especially on how they are using solar protections. So on this graph, you can see different configurations of solar protections and overhangs for the different building designs. And also indoor air velocity. So this was also a very simplified approach in which we set the indoor air velocity to 0.1 meter per second and one at 0.4 to assume that there is, for instance, ceiling fans. If we have found in the literature that ceiling fans should not be used when the air temperature is above 35 degrees. This is to keep in mind, but we have not considered this in this first approach analysis. Just to say that the influence of the occupant behavior is very important, and the discomfort can be greatly reduced in terms of degree hours, as we can see on these slides, even with acceptable indoor daylighting levels during the day. Finally, as perspectives, this is just to say a word on what is the work currently ongoing in the Annex 80 on building thermal simulations that will probably be presented in future webinars. That a framework of different stages of resilience was defined with different, so the building being an object with its own vulnerability, and then different stages of resilience that are consecutive after one or several shocks. And within the Annex 80, we want to analyze different shocks, such as different extreme heat waves, either the most intense heat wave, either the longest heat wave, and then also a combination of different shocks with some power outage for buildings that have active resilient cooling strategies to assess the resilience of these active cooling strategies. And just to quickly conclude, the methodology I had presented was with this new objective to integrate into building design, to think of using future heat wave weather files to analyze and minimize this heat stress risk, and to really think about it during the building design and not after once problem occur in buildings. And I also want to emphasize that really a combination of different mitigation and adaptation strategies will be needed to attenuate the climate change risk and this heat exposure risk. And it must be a combination of mitigation strategies at the urban scale, of the building envelope, of the different ventilative cooling systems, or also active cooling systems and occupant behavior. And yes, that's it. If you want to know more about my work, you can check out my PhD thesis or ask me more questions during the chat.